This section deals with color perception. Now that's how it's usually phrased, but color perception is a little bit misleading. What we actually do is make color construction. Our brain constructs colors from the perception of light frequencies. The color itself, redness, blueness, greenness, and so on, doesn't actually exist in the world. All that exists in your mind, exists in your brain. Your brain takes light frequency information and color codes it, makes sort of a schematic of the world that includes all these colors. We are so used to thinking in colors that we don't think otherwise. And only if you were colorblind would you have any sort of sense at all that colors are not in the world. There are, of course, many people who are colorblind, and I have a great movie on that at the course website. The point, though, is that your brain is constructing the colors from frequency information about light frequency data. It's getting that from the cones. The cones convey, by their firing patterns, their excitement, in certain frequency ranges, they convey information to the brain. Your brain takes all that and maps out the colors. It's always been intriguing to me that, red doesn't exist in the world. Well, where did red come from? Why is your brain encoding redness instead of greenness? Why isn't the light frequency of redness encoded green? I mean, how did that ever happen? And why is it so consistent among us? I don't think many people disagree on the color of something. Obviously, there can be some subtle disagreements about how colors are, but if something's bright red, everyone kind of sees it that way. There have been studies that show that there are small differences in color perception, but they're very small. Most of us don't have a sense that we vary much in that. Now, if you ever talk to somebody who's got red-green color blindness, and this is a genetic trait that's only prevalent in men, if you talk to somebody who has this and ask him what he sees, you will begin to get an appreciation for the way in which his brain has constructed the world in a different color pattern than your brain. And those folks with red-green color blindness tend to see the world in what you refer to as blue and yellowness, but it's not the same blue and yellow that you have. They do make a distinction between blue and yellow, but they also try to make distinctions between red and green and so on, because everybody around them has told them, well, apples are red. And, of course, they have no sense for what redness is. Apples do seem different than oranges to them, and so when they conceptualize the color and the color differences in those objects, they have a whole different perception of colors than you have. From that, you might get some idea of how variable color is. The point, though, is that the color designations we make are translations of frequency information we're getting from objects, from the electromagnetic radiation off the objects. I think it's even difficult for us to think of light as electromagnetic radiation. When I'm looking at a object that's light's reflecting off of it, I usually don't think of that object as reflecting electromagnetic radiation like I would think of as a transmitter, say at a radio station, which is obviously transmitting electromagnetic radiation. But the part of the electromagnetic spectrum that we can see is called light. And there's no difference, though, between the electromagnetic radiation in that range of frequencies compared to, say, the electromagnetic radiation being transmitted from radio towers. They're the same thing. It's just that we don't have receptors for those frequencies that are used by, say, FM radio, or by radar towers, or by TV stations. Those are parts of the electromagnetic spectrum we cannot perceive, and so we don't see them as light. We don't see that as light. The part of the spectrum that we can see, we call light, and different parts of that frequency spectrum we map as colors. Okay, well, light is a electromagnetic radiation. Obviously, physicists and engineers have studied light for many, many years. In terms of what we're going to deal with, we mainly think of light as electromagnetic radiation that has a certain amplitude and a certain wavelength. The wavelength, which is the distance between the hillocks or between the troughs in the wave, that represents the frequency. That's telling you how often a hill is coming. And so that frequency information is what gets translated into colors. The amplitude of the waveform is what gets translated into luminance. So it translates into how bright a light is. Now, obviously, we have better capabilities probably for mapping colors than we do for amplitude. It's not to quibble about which is better, but we probably have a better discrimination of wavelength than we do amplitude. You can tell luminance, brightness pretty well, but luminance is not so important for primate vision as color is. Okay, but at any rate, they're dividing those two things, and now the rods, they don't give the brain information about wavelength. The rods give information about amplitude, so they tell you how bright something is. The cones give the brain information about wavelength and probably also amplitude, both combined together into one pattern of information that's being conveyed by the retina back to the brain. Okay, now we're going to go into a little more detail about what these are in terms of how they map to color. Well, as you probably learned before in your high school physics class, white light is broken down into sets of frequencies that are the colors. And you can see this if you use a prism. A prism is a device that makes the light go through a different medium, and certain wavelengths will go through easier than others. And when that occurs, it spreads out the light from its original white source into a set of colors. You know, the rainbow, like you see outside. That's water crystals in the air doing the same thing. Well, what's happening is white light is being divided into these colors, but white light is just the perception we have of noise. It's all the frequencies blended together. So when we perceive noise in the electromagnetic spectrum, we construct that as whiteness. Now, it was none other than Isaac Newton who figured this out, and Isaac Newton was an interesting character in the sense that he was a very isolated, very inwardly directed person, and he was trying to solve this problem of what light was, its nature, its character, and so on. And he was sort of kept in his little room at Cambridge, and he made his room completely dark with a little opening in a curtain. They let a beam of light in, and then he put a prism to that light, and he saw the rainbow. Then when you put a prism to the rainbow lights, the redness, the greenness, the blueness, and so on, he noticed that those would not break down further, that the red light would not break down into some other spectrum. And he reported that to the Royal Academy and to his colleagues, and that was a very interesting thing. It led him to, these studies of optics led him to improving the telescope, which he used to, which others actually use. I don't believe he actually used the telescope that much that he invented. He redesigned the telescope, understanding this role of bending light, and others used it to observe the planets and the stars better. It was a big improvement over Galileo's invention of the telescope, and it was used to map out the path of the planets around the sun. So his initial studies, though, had to do with how light was broken down into the spectrum. He also did things where he, was, like I described before, where he was studying how movement of light sources and after images and things like that. He was very intrigued by light and very intrigued by color perception. He also used light to create sundials and timers, and he realized that the path of shadows around objects could be used to time things, and they were actually an indication of the movement of those objects, like the sun and the moon and so on. And he understood that there was a relationship between the movement of these bodies and how we calibrate time. But at any rate, he discovered that white light is broken down into these colors. Now, I think actually this is a great example of how the brain is constructing a color. When you hear noise in the auditory modality, so if you're listening to the radio and all of a sudden it turns to noise, or you're watching television and that goes to speckles of noise across the field, you tend not to perceive that as whiteness. But when electromagnetic radiation in this part of the spectrum gets blended together, where all the frequencies are turning to noise, your eyes, when that falls in your eyes and your brain construct that as whiteness. And so that's how white light is defined. And there's even a phrase used in radio transmission referring to pure noise, if something's purely random, as white noise. Okay, remember before when I discussed refraction and reflection and things like that, there was a phenomenon of reflection, and this phenomenon is also something you probably learned about in high school physics, but it's relevant to how we perceive color. The point of this slide is that light information, when it falls on a colored object, what you're actually seeing is the color that's reflected from the object. The object, its chemical properties, its texture, and so on, is absorbing all the other frequencies except what you're seeing. So if you see blue paint, it's because the blue light is being reflected. The blue and green part of the spectrum is being reflected back to you. The red and the yellow parts of the spectrum are being absorbed by the object, by the material. And the same is true for the others. So a yellow paint is a pigment that absorbs everything but the yellow, and it reflects yellow, and that's why that particular part of the spectrum gets recorded in the visual field by the cones, and then your brain constructs that as yellowness. So colors are representation of the reflection of frequencies off the material. Okay, well, each surface, each object, will therefore have an object-oriented spectra that's associated with the light that's reflected from it. And here you see a graphic that depicts different objects and their light spectra. If you look at the left side, you see the light spectra of different colors of paper. So typing bond paper, real white paper, you can see is reflecting pretty much all the frequencies. Now when you reflect all the frequencies back to the viewer, your brain is going to construct that as whiteness. That's what makes something white. Now a gray card, as you see down here, is got the same spectrum, the same frequencies are being reflected, but it's much lower level. It's much lower level of luminance. The amplitude is much lower. And finally, black paper is reflecting all the frequencies except at a very, very low luminance. Your brain constructs that as black. Then as you go up in luminance, you have grayness, and then as whiteness as the luminance goes higher and higher, and the spectrum stays mixed. Again, this mixed spectrum is noise. It's the blending of all the frequencies. Now, in the right graph, you see different objects, and different objects that you're probably familiar with. Look at the spectrum of a tomato. A tomato doesn't reflect much of the blue-green part of the spectrum. It reflects a lot of the yellow and the red part. A cabbage, though, doesn't reflect much red. It reflects everything in the green and blue parts. An orange, as you might imagine, is going to be reflecting a lot in the red and yellow part of the spectrum and very little in the others. And a lemon is going to be very similar to an orange, except it's going to be a little more shifted toward the yellow part. We can see now that the reflectance patterns are going to be characteristic of the colors that we tend to think objects are. Notice, however, that they don't reflect just that color, that the color of an orange, for example, is mostly orangeness, but you can see where there's also some other colors in it. Tomato and cabbage and so on are also like that. Very few objects will reflect pure frequency ranges. I think we have worked, for example, to make paint colors and ink colors be as pure as we can make them. But that takes a very careful mixing of substances that only reflect a certain part of the spectrum. And I think if you measured still paint colors like this, you would discover that red paint probably still has a fair amount of yellowness in it. And that's just a property of the pigments and the chemicals that were combined to produce the mostly red color. Here you see the reflectance spectrum or a object spectra of different kinds of light. Tungsten light is a reference to incandescent, the tungsten filament in an incandescent light bulb. These are the conventional light bulbs that GE makes that you screw into a light fixture. And tungsten lights, the tungsten filament will radiate a spectrum of light that's very weighted toward the yellow and red parts of the spectrum. Sunlight is also weighted toward the yellow parts of the spectrum, but you can see where it's still almost completely white. We actually have in our lens a slightly blue-tinted lens so we can partial out some of the yellowness that's in sunlight. This is really important to know if you're in photography. And if you're in photography, there's also other kinds of lights. Fluorescent lights, for example, are biased toward the green-blue end of the spectrum. And one of the oddest things you can do, of course, these days people don't use film anymore. It's still important for photography, but in the old days, different kinds of film were biased toward different parts of the spectrum. So for example, like Kodachrome was biased toward the yellow part. A film like Ektachrome was biased toward the blue part, and Agfa film from the Germany was considered the most balanced in terms of representing the whole spectrum. And that's because the chemicals that made these color films all would, they're not perfect representations of the light spectrum of sunlight, and so they'll tend to be biased one way or the other. The unfortunate result of that is if you took a film like Ektachrome, which is biased toward the blue end of the spectrum, and took pictures of people in fluorescent lights, which is even further biased toward the green part of the spectrum, the pictures would all come out with a green-blue sort of tone to them. Everybody's skin would look a little more greenish than it should. And it's a bad combination. See, in that situation, a photographer should pick certain films or use certain filters on the lens that correct for the bias. And, good photographers, of course, learn all this, and that's why they take much better pictures inside buildings and outside buildings than you and I do. They know all the subtleties of how these biases occur given them the equipment they have. Now, these days with digital cameras, the really good ones, will control for this automatically. So they'll register the light meters in them will register the frequency spectrum of the light that's being shown to the camera, and they'll actually adjust their data collection so it matches a pure frequency range. The less expensive cameras don't do this, and you'll still get biases in color spectra. They are pretty small, though, because most of the bias came from the film that was used and not so much from the lighting conditions. But still today, if you take photographs with a digital camera inside a house using tungsten lights, regular incandescent lights, you'll notice that they have a light yellow bias to them, a bend to them. Things appear more yellowish in those pictures than when you take pictures outside or when you take pictures under fluorescent lights. Well, here's the general structure of the receptors in the retina. You can see where the rod is differently shaped than the cone. The cone name comes from the upper part of that receptor that's roughly cone-shaped, and the rod comes from just simple sort of rod shape of rods. Now, rods are going to be detecting luminance. They're going to be detecting brightness, whether it's bright or dark in the environment. They do this with a relatively high degree of sensitivity compared to the cones, but that's all they can detect. The cones can detect color spectra, and cones become specialized for different parts of the frequency spectrum. So you have cones that are red biased and cones that are blue biased and so on. And I'll get to that in more detail in a second. They get their ability to detect frequency differences because of dyes that are in the receptor that respond selectively to different light frequencies. And when they respond, they cause a different response in the cell. When, for example, there's a red light exposing on the cone versus, say, a green light or a blue one. So the cone, if it's a red cone, will respond to that red light, become very active, but be less active when there's a blue light present. And that's how basically how they work. And again, I'll get into more detail as we go along, but this is the basic structure of the two receptors. Again, there's a big difference in distribution in them. You don't have any cones in the peripheral part of or very few cones in the peripheral part of your vision, and they're all packed in that central area of the fovea. Here's a graph representing the distribution of rods and cones in the retina. Now, it's very important to study this graph and get the basic concepts down. It's not a very complex idea, but it is a specific idea about how they're distributed that you need to know. Okay, well, on the left there you have the retina, and you see that there are degrees from zero, which is the fovea. So as you go away from the fovea, you see you have 20, 40, 60, and so on. That's represented in the graph on the right. Now, the y-axis on the graph on the right is representing the number of receptors present in that part of the area of the retina. So let's go to the graph on the right. You can see where the cones, they're in red there. You can see where the cones have a very low level in the periphery. See where it's 70 and 60 and 50 and so on both sides of the fovea. They're very low level. As you approach 0, which is the fovea, the number goes way up. Now, if you look at the rods have a real high distribution, relatively high distribution in the periphery that actually increases, the density increases or the number increases as you approach the fovea. And then as you actually get to the fovea, it goes way down. So the rods, even though there are many of them present in the periphery, most of them are still in the more central areas. They're just not in the fovea. And finally, you see there's a blind spot there where there aren't any rods and cones, and that's where the optic nerve is leaving the retina, going up to the brain. So obviously there can't be any receptors there. Those are all the neurons that are coming off the ganglion cell layer to go back to the brain. So the important thing to remember here is this distribution of rods and cones. The cones are in the fovea, the rods are in the periphery. So sort of burn that into your mind, keep that very clear. And the fovea only contains cones and no rods. This graph shows the separate sensitivity of the cones. So you have cones that have a certain range of frequencies that they respond at a high rate to, and then a certain range, in other ranges they respond less so. And it's not a perfectly uniform thing. It's not a carefully calibrated thing. It's amazing that it works as well as it does. But you can see here where you've got, at the lower end of the spectrum, the blue end, you've got cones that respond to roughly 450 nanometers of wavelength. Then you have a green that's responding at roughly, say, 540, 550 nanometers. And then you have the red, which is responding to about a 580, 590 range of responses. Now, people with red-green color blindness, they're missing the red and green cones. They only perceive blueness and yellowness. The genetic factor in some males produces a defect in that kind of cone, and so they don't produce cones that are sensitive in that range. So their perception of color, or their mapping of color, is much more constrained than it is with people that have all three kinds of receptors. But imagine, though, just keep in mind, what if we had receptors that could respond to 700 nanometers and 800 nanometers or 1200 nanometers? Imagine if you had receptors that could see the part of the electromagnetic spectrum that's, say, in the radio range or the TV range. If you could, then you could look at a cell phone tower or a radio transmitter at a radio station, and you would see it glowing some color. Now, those colors have never been invented by your brain, by evolution. Why these colors, look the way they do is some artifact of evolution that makes redness, made greenness, made blueness. And I don't know what color would represent the FM range, but presumably that would be a whole different color. It's not even, in the world yet. Here's a nice simple schematic that's showing you how different color receptors respond. So here we've got S, M, and L referring to short, medium, and long wavelengths. Now, when the short wavelength receptors are very active and the other two are less active, your brain maps that as blueness. So that's the first condition there. In the second one, the medium wavelengths are very active and the others are less so. And your brain maps that as greenness. Then finally, when the long wavelength receptors are active and the others are less active, you map that as redness. Okay, what about yellowness? Where does that come from? Well, yellowness represents the activity of the medium and long receptors and very little activity on the short ones. Purple would be the short ones and the long ones. Essentially, that's going to be blue and red being active without green, and so you perceive that as purple. You map that as purple. And finally, when they're all active equally, that gets mapped as whiteness, as white color. And you probably don't usually think of whiteness as being a color representing noise. But when all the receptors are active, that means all the frequencies are in the electromagnetic spectrum, and your brain maps that as whiteness. So what is color blindness? Now, color blindness, again, is another misnomer, isn't it? It's not blindness for colors, because colors are constructed by your brain. It's an inability to map frequencies by certain colors, and an inability to perceive those frequencies. But it's not literally color blindness, because color is not in the world. Color is in your brain. Now, light frequencies are in your brain, and that's, of course, what's being mapped. Now, if you have different kinds of color blindness. There isn't just one kind. And, of course, you can have people that are called achromatopsic who don't have any color perception or any color construction at all. And the movie Island of the Colorblind goes into great detail about those people. Well, you can have a color blindness in which you're missing the red and green receptors. And if you look at the display here, you're looking at what's referred to as an Ishihara plate. And Ishihara developed these plates in which you've got equal luminance across these blobs, these circles. So the light level is the same, and they only vary in terms of light frequency. So here, if you've got red-green color blindness, you can't tell the difference between the orange and yellow circles and the green-blue ones. So you're not going to be able to see that number 74 coming out of the display there. For you, it's going to look like a continuous, homogeneous or complete mix here of those bubbles, and you're not going to see that there's any kind of structure to them, any kind of form there. That also reinforces, I think, how colors reinforce form perception, and I'll get to that in a second. But you can see now where the difference in colors is going to help me discriminate the 74, that form there, from the background. Well, at any rate, though, for color blindness, if you have red-green color blindness, then you only perceive blue and yellow. So you refer to it as a protanope. Now, you can see where you've inherited receptors that only let you see blue range and yellow range. And so subtle distinctions between red and green you can't detect. If you have deuteranotope type color blindness, you have very similar to the protanope, except that your range of discrimination is a little bit different. And finally, you have tritanopes, which is a very rare disorder, I believe, in which you have a shift of just blue and red. And it seems to me that would be a type of color blindness that the person might not even notice they have, because you can probably discriminate a lot of colors or a lot of light frequencies just having the blue and red receptors. And your perception is going to be very similar to a normal person. At any rate, these are the kinds of patterns you can develop along with the achromatopsia. And that's depicted very well in the Colorblind movie. The Island of the Colorblind is a movie made by Oliver Sacks, in which he goes to an island in which many people have inherited a recessive gene where they don't have any cones. And so their eyes don't produce any color receptors, and their world is very different from ours. But rather than tell you about it, I think you should just go watch the movie. He also covers a lot of other topics in color construction that I've mentioned in this presentation, but he does it in his own unique, interesting way. Okay, now we're going to go into some more detail about how colors, essentially how color perception is used to enhance form perception, and how we form boundaries between color areas, and we tend to reinforce those boundaries. Because again, the color perception is still in the service of form perception. So when you perceive colors, it's not just to perceive the color of a texture on an object, but also to perceive where that object ends and the background begins, or where other objects begin. There was especially in the sequence in the Colorblind movie in which the person who can't see any colors is looking at a bush with flowers on it. And it's a hibiscus plant with bright red flowers against a background of green leaves. Well, if I needed to, eat the flowers, if I had an interest in those red objects and operating on them, and I couldn't see the colors, it'd be very hard to make out the flowers in the background of leaves, since they're both quite variegated in their form. Color perception, though, allows me to clearly discriminate them, because the background is, vivid green, and the flowers are very vivid red. Okay, well, I'm going to be using other parts of my nervous system to map out areas of color, in a way that I can maximally discriminate form. Now, we do this all the way through the nervous system, from the receptor level all the way up through to parts of the visual cortex that do this. The first level that happens is in the ganglion cells. Now, the ganglion cells are going to be influenced by the amacrine layer and the horizontal layer and so on, using mostly lateral inhibition to reinforce contrast between colors. So not only do I want to perceive light frequencies, But I really want to perceive where they change, because that's going to be a very strong clue as to the contour of an object. So if I have a bright red apple sitting on a table and I want to pick it up and eat it, I need to know where its margins are in order to have my hand operate on that object and be able to operate on it, for some kind of survival value. So I need to know where the red is very strongly contrasted with the brown color of the table. Now you can imagine things being more subtle than an apple on a table, but you can see what I mean. The color contrast is going to be a very strong clue as to where objects are. One very interesting aspect of color perception involves opponent colors. And we usually I don't think about colors opposing each other, but in the nervous system you have receptors for each type of, each part of the spectrum. And as we have this dominant principle in the nervous system and how it functions, this dynamic balance between excitation and inhibition that produces perception, produces motor actions, and all the things that the nervous system does. Well, let's start with the grid here, the Hermann grid, that we presented before in the context of luminance and luminance receptive fields and luminance lateral inhibition and things like that. As you might recall, the lateral inhibition and luminance receptive fields contributed to the definition of lines and forms. It contributes to the margins between light and dark. It enhances those, increases the contrast between them. Now, the Hermann grid is a sort of a manipulation of this, and allows a demonstration of how inhibition and excitation work actually to produce an optic illusion. Because you look at this grid, you see the gray squares coming up at the intersections, but notice that's only in your peripheral vision where you have rods. If you look straight at an intersection, you don't see any kind of gray square. They're only in the periphery. Well, remember, this was caused by excitation and inhibition, and the next slide is going to be a model of this. Then what I'm going to do is transition to color, excitation, inhibition, and opponent processes and color perception. Now, the ganglion cells, which are the cells coming off the retina, the neuron cells coming off the retina, they can form themselves into receptive fields, and they excite and inhibit each other. So when you look straight on a display like this, you've got the dark areas and the light areas, and the receptors in each of these areas, now they're going to influence the receptors near them. The net effect is to produce a drop in luminance, here a 5. However, when you look off an intersection, the same set of receptive fields are there. It's just the top 3 are in darkness, the bottom 3 are in darkness, whereas in the previous one there weren't so many in darkness. The net effect here is to produce a 5.5. Now the 5.5 is obviously higher, and so you don't see a dark area. Your brain does not interpret that as a dark area in the one spot there. But at the intersection, you've got a drop in luminance relative to the others, and so that net effect produces a misperception. Your brain constructs that as a drop in luminance, some gray area there. This obviously is an artificial presentation to your brain. It does illustrate, though, how this process basically works. So the dynamic interaction between receptive fields that are near each other will cause, in this case, an optic illusion, but basically will cause a sort of a rarefication or a contrast enhancement of margins. And in context of doing that, obviously, you see contours better. And when it comes to color, what we want to see are color contrasts better. We want to see a contrast between green and red. It doesn't make any sense if we don't see those contrasts, because if the colors get all blended together, it's almost as if we don't even need color. It's not going to be an important discriminating characteristic of the scene. But whenever frequencies are discriminating, we want that enhanced. We want it sharpened. And this process allows us to do that. Now I'm going to go on to the color slides, or the color fields, and talk about them in the same way. Okay, well, here's a display that's going to allow us to see a color after image effect. And the color after image effect is going to reinforce the theory of opponent colors. Now, we've also seen motion after effects. Remember, motion, the waterfall illusion, is a motion after effect. Motion going in one direction primes the system for that direction. So when motion stops, since we've been primed the opposite direction, the opposite direction now becomes the way in which we perceive the stimulus to move. Well, the same thing happens here in color, a very similar thing. The ganglion cells and the cells in the lateral geniculate are interacting with each other, and they're producing a inhibition and excitation along margins. And when there's a color margin, you'll see a color afterimage effect. It's quite remarkable. Now what you're supposed to do here is look at this display of this flag here, and look at the white dot in the center, and stare at that for about 30 seconds. So you stare in the center, the white circle, and try to keep your gaze fixed so that your retinal image is just going to be the flag. It's not going to vary around. You're not going to have a lot of noise in the image by staring at the white circle. You stare at the white circle, stare at the white circle. Now look down, and what do you see? When you look down on the white background, you don't see an afterimage of, a random afterimage. You should see a red, white, and blue flag. Now that's kind of amazing if you think about it. I think of my vision operating this way, that there's opponent colors. Well, presumably what's happening is the balance now is being affected by saturating in one part of the retina one or two colors. So if I saturate the green here in a certain part of the retina, all those green cones are firing away like mad, telling me, okay, there's green there, there's green there, there's green there. They're very, very active. They get depleted or they get too active. Their response starts to accommodate. Then when I look down at the white, now white contains all the frequencies. So green, red, all these frequencies are in the light image coming from white. Well, the green, in a sense, has been fatigued. It's not firing as much when I look at the white as much as the red is. The red receptors are firing. So my perception, my brain gets a relative pattern of lower green and higher red. Your brain then interprets that as redness is there. And so the afterimage gets interpreted as a red, white, and blue flag. The opposite thing happens again with yellow and blue, or they're reciprocal, they're opposed. So that when you look down, you see a blue background for the stars. Now notice that when you look at the yellow and look at the yellow and you look at the yellow and then look down at the white, you don't see red background for the stars. You see blue, as if these two are in opposition to each other. So red and green are in opposition. They must be linked somehow by the ganglion cells responding, and the blue and the yellow must be linked somehow. And this is also a interesting feature of our general perception of colors. Try to imagine red mixed with green. So what's red and green mixed together? Well, I think any artist will tell you that if you ever try to do that, you're just going to get muck. There is no color that represents the mixing of red and green. If you mix blue and yellow, you get green. So the problem is only really in imagining red and green together, because they're opponent processes. They don't mix together to form a blended color. And however, blue and yellow do mix to form green. Now you notice that green, your receptors are red, green, and blue. That yellowness is not something that's represented by a single receptor. It's going to come up by a relative firing pattern. And your brain interprets that relative firing pattern as yellowness. But it is opposed to blue. So yellow and blue are complements, and they're in opposition to each other. You notice that a lot of, very sort of clear patterns of color, like colors in logos or school colors, there's a lot of yellow-blue school colors because yellow and blue are complements to each other. They contrast real high. And so when you make school colors, you want them to contrast. You want them to be bright and distinctive. You don't see a lot of school colors that are yellow and green because yellow and green will tend to blend. You want to see yellow and blue because they clash. They have a contrast. At any rate, for some strange reason, and probably just a factor of how the nervous system works in general, which is still not clearly understood, color perception is an opposition, in the same way that motion to the right or the left is an opposition. And we see that also in the motor system, which I haven't gotten to, obviously, in this class on sensation and perception. But what happens is the nervous system is designed to be active all the time. It's not designed to be turned off and on like a computer is. And so your nervous system's on all the time, and so perception and action and things like that are always a representation of dynamic balance in the system. That's how it controls and modulates activity or perception and so on. That's the only way neurons can function, because they can't turn off. They're always going to be on a little bit. And it's when they get real active, that means something's happening. When they slow down, that means less of that is happening. But they're always on to some degree. Your whole nervous system is always up and firing some. And it's dynamic balance that produces function. And opponent processes in color represent a balance between different colors. There's a balance between red and green. There's a balance between blue and yellow. Here's another display that shows a color after image when you look at it long enough. Look at this display right in the center. Look at that at about 30 seconds. Then look on to a white sheet of paper or a gray sheet of paper, and you'll see a color after image. It's very dramatic. And again, it shows the dynamic balance between red and green and blue and yellow. Okay, just to summarize this, the early steps of perception involving the lateral geniculate cells and the ganglion cells and the receptors in the retina involves this basic model. This is obviously a simplification, but it does show the three basic steps. You've got receptors that are going to be active or inactive. So they get excited. They have dyes in them that excite the receptor and excite that system, and ultimately the ganglion cells, but excite that system when light of a certain frequency is present. So if you have a green cone, it's going to get active when that green range of frequency is present. Then you have opponent cells. Okay, so that green one gets active, but it's going to be inhibited by the red. So if there's a red frequencies in the light, there's going to be a balance there between red and green, which results in the color you actually see. And also there's a balance between the blue and the yellow, so that you have this dynamic balance between these reciprocal inhibiting processes, exciting and inhibiting processes that produce the information your brain uses to construct whatever colors are in that part of the visual field. Now the opponent cells produce these after-image effects and the simultaneous contrast effects, and this information is then what's sent to the brain. But basically what's happening is you have this early processing, this rarefying the contrast see between red and green, between blue and yellow, so that what gets sent to the brain is a sharpened image, color-wise, of what's there. Just like before, when the image was sharpened luminance-wise, now it's going to be sharpened color-wise. And so that the brain gets information that's not exactly what's in the world, but it's an image that actually facilitates its work, which is to find contours, find shapes and forms, so that you can act on these shapes and forms because you know where they are. Well, this graphic shows how an opponent process might work in a very simple network model. Here you've got the short part of the wavelength, the blue part, the medium part, which is the green part, and the long wavelengths or longer wavelengths, which are the red part. So you have receptors that are responding to each one of these ranges of light frequency. Then you have ganglion cells that are connected through the horizontal cells and the amacrine cell network in the retina to produce these patterns of excitation and inhibition. Now remember, inhibition is represented by a T intersection here, and excitation is represented by this sort of V-shaped intersection. Let's go over the right part where you've got the long wavelength receptor on the right side of this schematic here. The long wave receptor has a connection with the ganglion cell, and when it's turned on, it excites that cell. It also excites an intermediary cell labeled A there. So it's going to be sending stimulation to both those when it's stimulated by a long wavelength. Now, if that's all that's there, if it's just red light there, then the ganglion cell sends that information downstream to the nervous system, and you perceive a lot of redness. But what if there's some green light in the imagine the light being exposed here is sort of gray or white light, where both these are going to be stimulated. The medium range receptor is going to stimulate A, but it's also going to inhibit R plus G minus. Okay, so the green one, which is the medium range, is going to inhibit if it's there. So if light stimulates that receptor, it's going to inhibit the red receptor. So now you've got this dynamic balance now between the red and the green receptors that's producing a net effect on the R plus G minus receptor. Now notice that also, if A is stimulated by M or L, it inhibits the short wavelengths. And so you're going to have an inhibitory process that affects the perception of blueness. And so if yellow is present in the light, so that'll stimulate or green, that range of light is going to stimulate the M, which stimulates A, which inhibits the B plus Y minus one. Now you can see if all this is sort of chugging along here, you now have this dynamic balance between red and green and blue and yellow being conveyed up to the nervous system for processing as to what exactly your brain is going to do to map the color onto that part of the receptive field. Now, your brain interprets these firing patterns and then has a model for how to colorize the displays so that you can see red or green or blue or all the different colors that you see. This will tend, however, to rarefy the colors that are there, so that if it's a strong red stimulus, you sort of see that as extra strong redness, even if there's a little green in it. The big stimulation of the long wavelength will cause that red plus green minus ganglion cell to fire. If there's not so much red in it, then it won't fire so much. Or if there's green and yellowness, it'll fire a little bit less. Your brain is getting all this information from the firing pattern and somehow puts this together into, okay, I'm going to colorize that part of the retina, red or green or yellow or orange. And this dynamic balance changes as you move. You can just imagine the complexity of this as you move your head around, your eyes around, seeing different colors in different parts of the retina, all these receptors firing like mad, trying to give the brain information about the external environment. It's an amazing system, and I'm always impressed that it doesn't break down more often than it does. At any rate, this phase of it, the color perception, is very similar to the luminance contrast that we saw before. And the end result of this is really to enhance the margins it's almost like the brain wants to colorize an image that you're seeing so that you can make distinctions between objects better. If it doesn't colorize it, all you've got is luminance. Or if it's not sharpened this way, you're just going to have a sort of fuzzy margins between the red and the green. You're not going to have real sharp ones. And the sharp ones allow you to see forms that are red or green, and that's certainly much better than seeing the sort of error that's actually in the frequency distribution of the light itself. And here you see depicted a schematic with firing patterns associated with ganglion cells in different parts of this system. So here it clearly shows you kind of a schematic. That's exaggerating the effect, I think, to make a point, but that's fine. Well, let's go down the rows here. You can see the spontaneous firing rate of all these ganglion cells is that rate that you see at the top there. Now, that's a really good point because it indicates the nervous system is never off. See, it's always a level there of firing. And it's going to be the dynamic balance, up or down from that level, that's going to produce modulation or perception. Now, when you see a blue light, you see a pattern here. This is a 45 nanometer blue light, so it's pretty blue. It's very blue. You see that the blue-yellow, you get blue plus yellow minus. Well, if its firing rate's going up, that means it's being stimulated. So it's overcoming the inhibition, or the stimulation is just so blue that it's got a high blue rate. Well, blue is stimulated, so you see where the blue plus yellow minus is that section is firing. So that influence is producing a higher firing rate because it's very blue light. Notice also that the green plus is firing because green and blue see are in that part of the spectrum. The red in inhibition, though, is very minimal. So there's a lot of inhibition of red. There's a excitation of green. Now go to the other two. The yellow plus, this is a very blue light, so there's no yellowness in it. And you can see there that the yellow plus is not firing at all relative to that pattern. And then the red plus is also not firing. So basically what's happening here is that yellow and red are being inhibited, and blue and green are being excited. And so your brain says, okay, there's a very blue, very, very blue light there. Now imagine if you lightened it up. You took the blueness and you made it lighter blue. Well, that introduces white light, more noise into the perception. And so you're going to see more activity of the Y plus B minus and the R plus G minus because those frequencies are actually in the stimulus. And your brain is going to interpret that and say, oh, that's a lighter blue. And the perception is now going to shift from a very vivid, saturated blue to a much lighter blue. Now, if you look at the others, you see similar patterns for the other colors. So when green is present, blue plus is low, green plus is very high, yellow plus is very low, and R plus is very low. So you're seeing green. Now the yellow is interesting because yellow is not a single receptor responding to produce yellow. Yellow is you got this green plus receptor and the Y plus receptor are very active, but you can see where the blue plus receptor is very inactive, and the red is very inactive. And your brain says, okay, that must be a yellow thing there. That frequency is represented in the stimulus. And then finally with red, you can see is shifting over there as firing rates are associated with redness. You can see where yellow is present somewhat, and red is very present, but green and blue are not. And so the firing rates are going to show. Now see what this is doing though, you notice that what's happening is it's enhancing the contrast. It's enhancing the, if there's a vivid blue in the stimulus, you see that very well enhanced. There's no doubt in the system about whether blue is there or not. And there's even an enhancement, almost an exaggeration of that pattern, and a real inhibition of the other colors. And so the brain interprets that as very vivid blueness. Now, so that means that the colors that are actually out in the world, or the frequency ranges that are actually out in the world, are being sort of schematized by the brain. It's sort of like you took a vivid crayon in blue and you colorized it, like a colorized movie where they put in colors in a black and white movie. Well, imagine now that's actually a pretty good example because colorized movies are exaggerations of the color. They don't really look that natural because they're not made with a natural color process. It's like somebody went in there and colorized it, and so or colored it with a paint or something. Well, when they do that, you have a tendency to rarefy the color, rather than having the full range of blue, green, and these complex colors that would appear naturally in a film. You've got somebody sort of mapping very discrete colors. Okay, this is flesh color. Now, obviously, in a movie, you're going to have all kinds of flesh kind of colors, and you can't have a generic flesh color. And once you do that, it begins to look like it's a schema. It's not a natural, complex, noisy, muddy-looking sort of color. It's a rarefied flesh color, and the other colors are the same way. And so a colorized movie is doing somewhat what your brain is doing. Your brain is not doing it to the extreme of a colorized movie. But the frequencies that are actually in the world are much muddier and uncertain than what your brain does, what your brain gets from these systems that rarefy the color and try to make it as clear as possible. In the end, though, your perception is better of these objects if your color distinctions are made clearer. It's almost like you've got this Photoshop filter that is filtering out certain colors and enhancing others so that you got a much clearer picture, much sharper image or distribution of where the colors are. Okay, the final concept I'm going to introduce in this presentation is color constancy. Now, color constancy is a reference to the fact that we tend to perceive the same colors given different kinds of illuminance and given small shifts in the ambient light frequencies that we see. Now, our nervous system is basically primed to perceive sunlight, which is more or less continuously white. Now, it is shifted a bit toward the yellow range, but it's a very small amount. So we tend to, our nervous system evolved in the context of sunlight. We didn't have any artificial light until the 20th century. And our nervous system is built around this idea that basically colors stay the same regardless of illuminance. So if I see a red apple outside and it's bright red, and I bring it inside, the luminance changes, but the redness shouldn't change. There's this fundamental assumption that color frequency information essentially should not change. Now, your nervous system is primed with this. It's designed like this. It's going to see the same colors under different luminancy no matter what. Now, I remember when I was in high school, I did some photography for an architect firm in the summer. That was my summer job. And I learned a lot about how different films responded to different color ranges and how different artificial light conditions influence the color distribution. For example, we would commonly go into, say, a school or something like that and take some pictures in fluorescent light. And for us, it looked natural. I don't have a sense that when I was in a room full of, that was illuminated by fluorescent light, that there was anything wrong with it. It looked like it was pretty much natural sunlight. Then we would take the pictures back to the dark room. We'd develop them. We discovered that they were all green tinted. Everybody in the picture looked kind of green, and that's because the fluorescent light was shifted toward that direction. It wasn't natural light. Now, incandescent lights are shifted toward the yellow direction. So what photographers do is they put filters on their camera lenses to try to compensate for the shifting that's done. So the film, in a sense, only sees a natural distribution of color. Now, in your perception, I think it's probably the same. When I was going into those rooms, illuminated by fluorescent light, I was keeping all the colors the same, even though there was a slight shift in all the frequencies of light that were being exposed in that room. My red was still the red I expect to see in a red apple or a red tomato. I don't have a sense that, well, it's slightly green now or shifted toward that range of frequencies. My brain compensates for the small change. Now, if it's a big change, if somebody puts a pink light bulb in the room and it turns everything pink, you do perceive that shift in color. But small changes don't seem to affect color perception, and small changes in luminance don't. I think actually large changes in luminance don't. Our brain compensates for those things. It keeps colors the same, and unless there's some really extreme circumstance, it keeps colors constant. Now, this is a really nice example of that. This is a color constancy illusion, and it blows my mind every time I look at this illusion. Now, looking at this cube here, you don't really have that much sense of an illusion here, and this shows you how color constancy works given different kinds of luminance. Now, when you're looking at this cube here, what you should do is go get a piece of paper and cut a very small hole in it, like you punch a hole like with a hole punch, that size of small hole. Then put the piece of paper up in onto the brown square that's on the top of the cube. So you're looking at the color of the brown square just through the little hole in the paper, and you can't see anything else in this display. Now move that hole down to the orange square that's in the shadow, in the middle of the side of the cube that's in the side of the cube that's in the shadow, and just observe what happens. You should observe that those two are the same color. And when you take away the context, your brain perceives the color accurately in the shadow. And it turns out that the orange one at the bottom there is exactly the same color as the brown one on the top. Your retina is responding to those as if they're the same color. Your brain says, nope, wait a second. That orange is in the darkness. If it's in the darkness, if brown is in the darkness, it must be lighter, because brown is dark orange. And so your brain has memories of this, experience with this. It wants to maintain this color constancy. So if it's in the darkness and it's brown, it must therefore be lighter. It must be a lighter color. A lighter brown is orange. And every time I look at this, I'm thinking, okay, I'm going to make that orange one brown, and I can't do it. It's always orange sitting there. But when I look at it through the little hole in the paper, it somehow miraculously appears brown in the little hole, but orange when I look at it in the shadow. And this is, I think, is one of the greatest examples of color constancy I could ever think of. Your brain is compensating for the luminance and making a judgment, making an inference or deduction. It's making some kind of decision that the luminance is going to qualify the color, and so if it's in darkness and it's brown, it must be a light brown, which is orange. And I defy you to try to perceive that one correctly. It's always going to be misperceived, and it's just an amazing thing. Actually be kind of cool if somebody would make a Rubik's Cube an actual object. See, this is a 3D model that was made with a computer program. If someone would actually make one of these, because then if you turn it around in regular old room light, you should have the same misperception of a real object that you're seeing here in a model. At any rate, color constancy refers to this bias, this tendency of your brain to map colors in a very consistent way, consistent with this experience with sunlight, your genetic background, and how your color vision evolved, but also your memories and experiences of objects predispose your brain to making certain color judgments and maintaining color constancy.